All right, good morning and welcome to today's class where we will deep dive into another interesting concept today. We've been dealing with machine learning and AI, and today we want to go deep into another interesting topic in machine learning. Okay, so it's a very sensitive one. It's very sensitive in the sense that we have a lot of silent questions to answers and discuss about. So, and also I want to quickly commend you all for your last projects on designing and working on machine learning model that predict the that predict students' performances based on the time they put into study. You people perform all great in that project, and I must commend you for that. All right, so at least with that, with what I saw from the project, it means that you really understand what we are doing and the effort is not wasted. Okay. So I'm super proud of that. But today we'll look at yet another interesting concept, which we will get to see how it is, see example, practice, coding example, real life scenarios, and all of that. But before I start, just some reactions that I'm audible enough and you can hear me.
You're audible.
All right, all right. Beautiful. Okay, so as usually, like I do lately, I create a document for every class to help you understand. So I'll be giving out a very general explanation on it. Then we check out how it is worded, all the relations in the document, and just to keep track with the document so I don't miss out anything. So the important part about the document is to help me keep track so I don't forget or leave anything untouched. All right, so today we want to deep dive, although we already had prior knowledge about it due to previous classes. So if you're not there, you can watch recordings of the class. So today we want to deep dive into the concepts of supervised learning, algorithm, and machine learning. Of course, by now you should know what supervised learning is at the very shallow level, but we want to get to know the nitty-gritties and all the things inside supervised learning. All right. So just this below is what we'll be looking at. So as you can see, these documents provide an in-depth exploration of supervised learning algorithms, covering the fundamental concepts of classifications and regressions. We did that, but we'll even dig into it more. Delving into common algorithms like decision trees. Come on, how is it taking me there? Decision trees, random forest, support vectors machines, and discuss model evaluation metrics such as we look at accuracy, precisions, and recall. Furthermore, it outlines practical projects involving implementations of a classification model on a well-known data sets like the popular IRIS data set that we've been working on. So this contains a lot. So we'll be looking at it one by one, and that's why I said it's going to be a very long class, a long talking class, and practical. Yeah, because we get to see the coding examples, how it is done, and how it is applied. So sit tight, get your mind ready, and as usual, you need to imagine it as I'm trying to explain it and relate it to real life scenarios. You need to imagine it and try to think and feel with me. Okay, so let me quickly, before I even get to what is there, the technical stuff, let me take your mind to what you've been using daily. Now, just come down and listen to this explanation. You could see yourself firstly. Let's say a banking sector or a microfinance bank that deals with distributing or issuing out loans. And the afterwards, I'm trying to explain or bring to life decision tree by this analogy. Right. So suppose a bank has to approve a small loan amount, right? A small loan amount for a customer and needs to make decision quickly, because before you need to issue out this loan, you need to take out some decision, get to analyze something, get information. Should I give this loan? Will this customer be able to refund the loan at a stipulated period of time? So before they issue out the loan, they need to make decisions. So the bank, first of all, checks the person's credit history and financial condition and finds that these particular customers haven't paid the older loan he or she collected yet, based on this check that they do. And hence, with this record, that the from the history of from the customer's previous history or credit history, that since the financial conditions and find out that that particular customers haven't paid the loan he or she collected previously. So with this, the bank will like hence reject the applications of issuing out the loan. But to that effect of what they do, they just took a singular decision, right? But here's a catch to that decision they took. The loan amount was a very small one, right? For the bank's immense offer, right? And they could have easily approved it in a very low risk move. Therefore, the bank lost chances of making money. I don't know if you follow. They just took a very narrow or single decision. Okay, with the fact that the customer did not pay out the other loan, or the financial history of the bank is not so good, without putting other things into consideration, voila, they just decided not to issue out the loan in a very simple way. Now, in the other way around, you could see that nowadays, like now, a few days later, another loan application comes. Just follow me. But this time, the bank comes with a different strategy, a multi-decision making process. So sometimes it checks for credit history, which the previous one did not do. It checks for credit history, and sometimes it checks for the customer's financial condition and the loan amount. Just putting so many things into check. Then with this, they now compare that the advantages outweigh the disadvantages, or the risks, the opportunity they stand to gain outweighs the risks. Then the banks now combine all these results from the multiple decision-making process and decide to give the loan to the customer. Now, this is another catch. Here, the bank profits from this method, even though it looks longer due to several processes that they need to put in check. All right. So it's longer than the previous one, right? But this is a classic example. This is a classic example, right, of collective decision making, outperforming a single decision making process. So now the question is, do you know what these two processes represent? All right, so this gets to answer what is called decision tree when we get there, and random forest. So I need to quickly bring out that example quickly so that you get to know some things about it. All right, so that is that, and let's get into practice. Okay, so these two are under supervised learning, and of course, from what we did last week, you know that supervised learning is is a training or is a learning process whereby the features, I'm going to use some terms now because we've been doing it, I've been explaining, whereby it's supervised learning is a learning or training process which includes what there is a feature and there is a label. And by feature, you know that these are examples that should be trained on. And the label, we know that the labels are the output. I needed to quickly take you back to weeks back that we did this, right? So you know what supervised learning is? That it's a learning process. That day I gave out a very simple illustration that it's like a student who is preparing for a particular exam using the past questions that has answers in it to learn. So at the end of it, if it gets to this to write the exams, it will get to beta because it's learned from the examples, which are the features in our case, and then again the answers were also in the past question, which in our own case is the level. So I needed to quickly add that connections. And you will, since in that last week, watch recordings if you were not there. Since in that last week, we look at classifications and recreations and we saw what that classification does. What it groups things into category of yes or no, bad or good, a fraud or not defraud, and all of that. And recreations has to do with numerical classifications where you need to take out a model to check the energy used in a specified form. So that is just taking you back to last week and classes we had. Okay, so let's see what we have here. Supervised learning at its core involves learning a mapping function from an input to an output base. You know what that means? Input includes a whole lot of things. The examples, like the features there, and what's the output based on label training data. You know what the label is. So the nature of the outputs determines whether the task is a classifications or the regressions. All right, and then again, in still that previous classes, I made mentions of determinants or independent factors and dependent factors. So I made mention that the examples or the features are the determinant or independent factors, while the output or the result is the independent factors, which of course the result will always depend on the what input, on the examples we have, on what is the features, of course. So the results depends on the example. That is when I made an illustration of a house price. So for you to determine or know if the house is going to be costly, there are some determining factors, which of course in our own case we call it features, and you know that the features are the examples. So this could include where the house is located, is the house and the house age, if it is a new house or an old house, is the house does it is it close to social amenities? Is it accessible? And all of that. Does it have constant light and water? So those are the determining factors. So if these things are put in check, we now decide, oh, if the house is going to be costly or not. So those are it. And in our own case, when these two are under supervised learning, classification and regression. So it is the output and all of this will determine if it is classification or regression problems. So for the house case that mentioning the price, you know that regression has to do with numerical things. So it is the output. If it is classification, you could check for emails spamming, for financial and fraud detection and all of that. You know that it's under classification. But if it has to do with numerical values, the output and the results, you know that it has to be regression. So that was just a very quick overview so that you get to relate what
Please,
you
can
are
you take
doing.
that last point again? That's one you just differentiated.
Okay. Where did you lost me, or where did you started getting confused?
No, not like I'm confused. It's just the last point you made, you were to
Okay,
clarify
okay,
the
no problem.
difference.
Okay, although I said we deep dive into this the last class, so I was trying to take your mind back there so that it can add some connections to what you'll be doing today. So we looked at this classification and regressions are under supervised learning, right? And of course, you know what supervised learning is. So for these classifications, it's groups, or its goal is to predict what categories or group things into. For example, we have your email spam, if you are spammed or not spam. Then for regression has to do with numerical applications and all of that. So it is the end result, right, of this classification you now determines if what you are doing is classification or regression. And for this regression, it has to do with numerical values, numerical applications. I just said an instance with house, with getting a house, and maybe you want to define a model that checks if the house is going to be costly or what. Of course, you know that the end product of it is going to be the price, and the price is what numerical values, so it falls under regression. But if it's what can be categorized or grouped, it falls under classification. I don't know if you get it. For the classification, it could be rich or not rich, spammed or not spammed, good or bad, a black or white. Things you just group it into categories and all of that. So I believe that makes sense to you, though,
Yes,
Sandra.
yes.
Okay, so I was just trying to establish a connections between what we have been doing previous weeks or previous classes with what we'll be doing today, so that it makes even more sense to you. Okay, so that is that. So let's get into it one by one. So in classification, the goal is to predict, yeah, like I said, is to predict a category or discrete output. So the model learns to assign input data points to specify classes or specific classes or categories. And examples of it is what is spam detection. So for the spam detection, we have email spamming, or classifying emails as if it is a spam one or not spam. You could see now in the categories now. Or image recognition, identifying objects in an image. Is it a cat? Is it a dog? Um, it's in here. And another one is medical diagnosis. Okay, these are examples now are under classifications. So it determines if a patient has a particular disease based on symptoms or not. So you could see that category. This patient has been diagnosed of this a particular disease or not diagnosed. This email is spammed or not spammed, right? So these are just visuals of what types of classification tasks. Spam detection classifies email as spam or not spam. So this it's enhanced email security. Image recognitions identifies objects in image, aiding um, visual analysis. And another is in the medical diagnosis, which determines disease based on symptoms, improving healthcare accuracies. Okay, so let's see regression. Of course, with the little overview I gave, you know what regression has to do with. So in regressions, the goal is to predict a continuous output value. The model learns to estimate a numerical value based on the input data. Numerical value based on the input. Okay, for example, is the house price prediction that I just mentioned that I talked about. So this estimating the price of a house is based on features. And by features, we discussed last week what features are. Features are examples or determining factors. I made mention of it, and they are independent, while what label, otherwise called output or results, are independent. So for the house price detection, So it estimates the price of the house based on features like the size, locations, numbers of bedroom. It could be the age of the house. Is it new or old house? Is it close to social amenities a, like hospitals, like school, like churches, like airports? Is there always lights there and all other cool stuff? So this, it will help you determine the price of the house, and you know that price has to do with what? Numerical value. So with this, with the reports you've seen now, that this one ends at the end of it, its output is numerical. So you now know, okay, so this is where I should classify it to, that it should be under regression. And for the email and spamming and image questions where it groups into categories, you should see that it should be under classifications. Okay, so next is stock, still under regressions examples. So next is stocks price forecasting. All right, so this one, it predicts the future price of stock based on historical data. Maybe you carry out analysis of in your, maybe, okay, let me use a supermarket for instance. They bought a particular, let's say two groups of products, let's say cream, let's say cream A and cream B. So from this month, they've seen that customers really patronize cream A instead of cream B. So with that, it can help them predict the future, that next month it is these two words, cream A, that customers would prefer. So with that, it helps them discover trends, okay, which also helps future market sales. So what this means that it predicts the future price of stock based on historical data. Another one is temperature prediction. You know that all these ins, like their label or their result is what's numerical, so it's under regression. So forecasting the temperature based on weather patterns. So these are that. So the key differences lies in the type of output variable. Of course, you've seen classification deals with discrete categories, while regression deals with what? Continuous values. Okay, so now let's look at a very important scenario, or how should I say, concept in algorithm. Okay, so this, we have decision trees, we have we have random forest. So we get to look at them. So for the decision tree, let me first give explanation before we get to the concept. So for the decision tree, it is a supervised, it's still under supervised learning, right? So it's a supervised learning algorithm that can be used for both classification and regression process, right, or problems. So the algorithm is built on a structure, or it's a model in a structure of a tree with decisions, nodes, and leaves. Now let me explain this. I already explained decision trees, but let me just give us. So a decision tree is a series of sequential decisions, right, which made to research a specific result. I just said give out a very live illustration on maybe a microfinance bank that issue out loan. So based on their decision, just a single one, and that of where they put out so many things into considerations. Okay. So with that example I gave from a microfinance bank, it gives you a real life applications on what decision trees is. All right. So it's, and for that, the advantages of it is that it's easy to use. It's just a one way something. It's easy to use and apply. So that is that, but let's go see how it is sorted in the documents. So decision trees are fundamental supervised learning algorithm used for both classification and regression tasks. They work by recursively partitioning the input space into smaller regions based on a series of decisions. All right. So how it works, just leave this, but pick out from what I say, although these are some characteristics of it. But let's see. So root node, the tree starts with a root node, and you should know that for you to start something, working on something, this root node should be what? A data set. Okay, so don't get confused. So the tree starts with a root node that represents the entire data set. That is one thing you should know. Another thing is for you to split it. So splitting, the algorithm selects the best attributes of the best attribute to split the data based on some criteria. Okay, so just leave this. I said these are the sample kidney impurity or informed gain. So for classifications or variance reduction for regression, we look at this. So just don't worry. Another is internal nodes. Each internal node represents a decision rule based on an attribute, and branches. So each branches represents what? Each branches represents how should I say, several things you get to put into considerations for that. And a leaf note, the leaf notes represent the final predictions, class level or for classification, and numerical values for regression. Okay, so this is just its cycle, decision tree algorithm cycle. I will leave this to you at the end of the class in the group, or you also find it in the video description when I get to. So it starts from the root node, which represent the data set. Sorry, someone just unmute. You want to ask question?
No, sorry.
Sorry?
No, I don't have any question. I was zooming it, so my hand pressed the unmute button.
Okay, okay, no problem. Okay, so this is just the cycle of what we discussed here. Get to look at it when I drop it for you. So now the advantages of it for the decision tree, it's easy to understand and interpret, just that one way. But then again, it does not put, okay, that is on the disadvantage when I get there. So it's easy to understand and interpret, can handle both numerical and categorical data. So based on the outputs, based on what you want. So for numerical, you know it's regression, and for categorical, you know it's classification. So non-parametric, meaning that they don't make assumptions about the underlying data distribution. So for the disadvantage, it's prone to overfitting. And the last class, I made mention what overfitting and underfitting is. Who can remind us? For a model to be overfitted or underfitted, what does it mean? Ah, God, my people. Okay, so it means for the overfittings, it means that the model overlearns, and with that gives out some error. And for underfitting, it means that the model does not learn enough. Okay, so that is when I even talk about from a modeling. I even talk about what the hyperparameter last time. For the hyperparameter, I made mentions that they are not what is in the data, but some of the things or settings the whoever is analyzing the data, or the scientist, the developer, is it's manually setting to make sure that the data does not underlearn, or it does not overfit or underfit. Just make sure that the models learns well, does not overfit or overlearn or underfit. Okay, so it's not overlearned or it does not underlearn. Okay, so that is that for next week. You can watch the recording. I just need to bring it back. So another thing under the disadvantage, sensitive to small changes in the data, because it's just one thing. So it's just sensitive to that thing. Okay, so can be unstable, meaning that small changes in the data can lead to significant different trees. So overcoming overfitting for this, because it's just a single one, maybe it takes into consideration just a single check. So if that is what it ends, it might overfit. Okay, so it's prone to overfitting. But let's see how to overcome overfitting. So pruning, removing branches that do not significantly improve the model. performance. So from this removing branches, what it explains that maybe you could have a for example, in getting a house and some of the features of getting a house, some you might add, does the color of the house or the house paint, does it really add to the house in price? No. If it likes, let the color be pink or red, it does nothing to the house. So these are things you take them out. The color house, you take it out. What what again will we take out? Okay, a very obvious thing there that does not add to a house price is the color. So one could like, have you ever heard someone when they're asking about the house, they're like, what color is the house? So these things that does not really add any significant meaning to what we do, we just take them out. So there are lots, but I just remember that colors. So limiting tree depth, restricting the maximum depth of the tree, and these are not putting in too much things. So you just need what is needed to for the model to predict or not, Okay, so setting minimum samples per level. So you require a minimum number of data points in a node. So just leave this node and all of these, that those terminologies, but you could, if you could picture it real, the way I'm putting that, there are some examples, there's some determining factors and some examples and all of that, it will really make sense to you. So now from the random forest, okay, let me even ask you, in the example I set up about the microfinance bank, where they put out one process in check and voila, they arrive into conclusion, and the order that they have to put so many things in checks, the customer history, the customer credit balance, and the amount of loan and all of this. So which one do you think will do better? Are we together? I'm throwing a question at you now. Which one do
Yes,
you
the,
think?
the one that has multiple checks.
Okay, so that is what random forest does. Okay, so this is that one checks for one thing, and for this random, it adds what it checks. It adds to it, and just as it implies, it puts so many things. Look at into checks and all of that. Just combining what this one did. Okay, so random forest. So the decision tree algorithm is quite easy to understand. However, a lot of people, including data scientists, use random forest. So it's a single tree, not sufficient for producing, that is for the decision tree I'm telling you now. A single tree or a single decision is not sufficient for providing or producing effective results. So that is where the random forest algorithm comes into play. So before I get to the document to see what is there, let me just give you this analogy. So random forest, you could see it as a tree-based machine learning. Let me add those things so you get used to it. Machine learning algorithm that does what? That leverages or based on what? Multiple decisions. So if you want to make it technical, you could add multiple decision trees. Okay. But if you take decision, it's not bad. So it leverages the power of multiple decision trees to make what decisions. So as the name suggests, it is what a forest. So that one, just take it. That one was a decision tree. Just take it as that. So this one, take it as what? A forest of trees or more trees instead when that one was one. But why do we call it random forest? That is what it is. So this is because it is a forest of randomly created decision trees. So what that means is that from here we saw that it deals with one node, where one node and all of that. So the random forest is what? Each node in this one, in the random forest, each node in the decision to work on a random subset of features to calculate out, to just check this, and arrive at an stipulated output. So the random forest then do what? Combines the output of individual decision tree just from that one. That one was one, but the individual decision tree, picture it as a forest, okay, to generate the final result. So what that means is that in real life, let's say you want someone to advise you, you now go to one person. that person gives you his or her own advice. But when you now go to a group of people or teams or an organization and ask them for advice, you see that advice from different people will not be anything compared to advice of one person. It will really make sense. So that is what random forest aims at achieving. So let's see with that example it should works for you, and let's see how it is worded here in the documents. Okay, so random forests are an example, yeah, just like a lot of things. We could say it is multifaceted, if that is the word. So random forests are an example in assemble learning method that combines multiple decision trees, maybe decision or from a lot of people from team, not from one person as a decision tree did. So it combines multiple decision trees to improve accuracy and reduce overfitting. And this overfitting was the problem of what the first one, which is the decision tree, just one. So this one it reduces overfitting. All right, so let's see how it does that. So I may mention that the process this what combines the output from a lot of people, but in our own case, let me make it tailor it to what we are doing. So it combines output from multiple or individual models. Okay, and we call these things this a multiple trees or models. We call it assemble learning. I just remember that so I don't forget. So if you want to get more accuracy, okay, more accuracy, more or more, okay, let me picture it to more people now, more advice. A lot of people gave you advice, and now assemble all the advice that they gave to you, and with that it can produce even more results than you want from one person. So that's real, and that is what random forest does. So let's see how it works. Bootstrap what bootstrap sampling. So this algorithm gets multiple subsets of the training data by randomly sampling with replacements, bootstrapping. So just if I say multiple subsets and notes, just picture it. This is the machine learning terms, but just try and relate it to real life scenarios that I am giving. All right. And just to know, there's something called, I just remember now. So this random forest use what is called use Python to solve a binary classification. And you know what binary is? They deals with zeros and ones. Okay. So that just came into my mind. I need to quickly add. You see it. Okay, let's get back to what we're doing. So tree building, for each subset, a decision tree is built. So, however, each split only a random subset of features is considered. This is the machine learning terms now. So compare this and take it to the real life explanation or scenarios I gave. So aggregation. For a classification, the final prediction is made by aggregating, zooming up in what I said earlier, assembling or collecting all the advice and add them together. So leave this aggregating is just add, but it's English for machine learning or terminologies, if I should say. So the final prediction is made by aggregating the predictions of all the trees. So in our own case, getting what prediction of all the advice they gave you. So example, majority voting, okay? Let's say we have a lot of people vote for one thing. You need to get a product, let's say product A and B, and you get to one person. One person says he or she likes product A. That is advice, or that is decision from one person. And you get to where a lot of people vote for product B. So that should make sense to you that there is something about this product B that is making everybody vote for it or go for it. So that is what this actually means, this majority voting. So for regression, the final prediction is the average of the predictions of all the trees. And if it is predictions, you know that it is numbers, numerical applications. So if it's what can be categorized, you know that is classification. Okay, so that is that for it. You could see bootstrap sampling, creating multiple data subsets. So you get to get people tree building, constructing decision trees with feature subsets. These should be examples, a lot of examples and all of that. So from all these one, you combine all of them or add all of them to predict the final output. So from the result, or let's say in our own scenario, from what I was saying, from the advice a lot of people have been giving you, maybe a lot of people tends to one thing. You just sum all of them up and get to the final output. And it's this your final output that you will decide if it's what, if it's classification or if it's regression. Okay, so advantages of random forest. High accuracy. Of course, you should know that high accuracy that individual decision trees that we saw. It reduces overfitting. Just make sure that the models learns well, not or it does not overfit. It provides future important estimates and can handle high dimensional data better in all form. So the disadvantage, of course, with all this process, you should know that it should be complex and all of that. So let's see. Disadvantages, it's more complex than individual decision trees. That is when it's for this, that is when it gets to applications and working on it. So it's more complex, can be computationally expensive to train, less interpretable than individual trees. So what this means is that a single decision tree also has its importance, and that its important is when you are working with a very small data, you can use that. But when it gets to complex or very big data, very complex one, you have to use random forest. So that is just the two things. Okay, so we get to see it's working before we even get to um what support vector machine and all of that. So for the parameters of this, you could see this n estimators is a parameter you see in the coding section where we get to practice. So once it is a parameter that denotes the numbers of trees in the forest. Maximum features, you know what features are, that they are examples and determining factors, you know. So this is the number of features to consider when looking for the best splits. And max depth is the maximum depth of the tree. Okay, so before we even get to see the coding example, we have something where we could check for the accuracy and all of that. So let me even discuss it first. Okay, and that falls under binary classification. Or let me just finish up the documents before I even get there so that I don't forget what is here. So SVM in full supports vector mechanics on machines, you see. So these are powerful supervised learning algorithm which uses both classification and regressions. And their aim, I'm just going to be a bit faster, and their aim is to find the hyperplane and separate data points in different classes. By hyperplane, it means that, let's say we have a very linear graph. By that, we've been plotting graph and something. Can I get a pen? Let me get Microsoft Pens. Pens. Is it taking time to come up? Pens, okay, yeah. I just want to illustrate with this. Okay, so this hyperplane now, it is a line. Let me just get something to draw. Let's say we have something like this. And I pick this color. So we have something like this. And we have a line. So let me get rid. So we have dots. I don't know if you can see all these dots. All these dots. Let me just use cycle. all these dots, all these dots. So these are dots, and I get here to get what. So these are lines or dots also. So it is this line that is called hyperplane. This line, this particular line that you are seeing. It's this line. So let's go see what it is. I just need to see some visuals about it. So an hyperplane in a two-dimensional space, the hyperplane is a line. Is a line, just what you see in a dimensions. So that particular line is what is called hyperplane. In the document I will share, I think it has some visuals in it that will help you see better. So I'll just send that. And the margin, so the margin is the distance. This margin, where is that my pens? So the margin is the distance now between this. That's the margin. So the margin is the distance between the hyperplane and the closest data point from each class. From here to here, and from here to this data that is here is what the margin. So support vectors, the data point that lies closest to the hyperplane and influences its impulsions. So for this, which is the closest in this, let's say this rate, and over here, we say it is this one. It is this one. I could not get a visual, but I have one document that gives it visuals for this, so you get to see. And kernel tree, the support vector machines can use kernel functions to map the data into a high dimensional space where it is easier to find, separating hyperlane and common kernel. Let me not just go this, you see it in the reading sections. This is just it's defining hyperlane, establish initial separating line or plane, calculate margin. So this margin is the distance that supports vectors. It's getting more technical. What is vectors? What is hyperplane? What is hyperparameters? You get to see. So these are just the examples, but this is what I'm more particular about, so that way we can discuss the accuracy and all of that. So before we get to here, let me give you a very general overview so that when we comes here, you're seeing formulas, so don't worry, you understand when I get back. So we could see that a binary classification that I talked about for what zeros and ones. So a binary classification task can fall under one or two categories. So it could be binary categories, which has to do with zeros. So where the number of class is 2. For example, when it's binary, we saw the email spam classification. We did that data. And another we saw, another under the binary classification is multi-class. I just remember that I need to bring in so I don't forget. Somehow I did not put it in this document, I forgot to, but let me tell you. So multi-class classification is where the number of classes is more than 2. But in binary classification, it was just 2. The classes is 2, but the multi-classes, just as the name implies, it's more than 2. So for example, what should I use? Let's say an e-commerce inquiring an email into 3 types. Okay, so these emails could be what they call shipping, could be returning, and could be tracking. Okay, you track your email. From that, you get to returns and you get to ship. Okay, so let me just give you a general overview. I'll begin with let's say binary. Let me still stick with the spam email classification, right? Where we can classify a list of email into 1 or 2 classes, which include spam or not spam. Is your email is spammed or is not spam, right? So I'll just take it out. Now from there, now it comes the accuracy of what I'm saying. So the most straightforward way of measuring a classifier performance is using what accuracy metrics. And by this accuracy, it measures how correct or how accurate the model is. So how less the accuracy is, its number shows that it's very accurate. So if it is big, the number, it shows that it is not so accurate. I don't know, that is the example I can give. So the accuracy is the given, is maybe the number of correct prediction. So if you want to total it now, you could take the total number of what you have, okay, and divide by the number of it. So what you want to take and now divide by the total number. So what it gives you is the total number of predictions. So from all your emails, you could now take from the email spam, you could have maybe 15 correct prediction out of 5 incorrect prediction. So for that, you could say 15 and 5, that could be about 75% accuracy. So you could just check that. So precision is how precise it is. Sorry, can you hear me? Let me be sure I'm not talking to myself.
Yes.
Okay. Okay. No problem. So we could see for precision, it could be how precise a model is. We could say maybe it's maybe positive value overall, or both positive and negative. So if you want to take for the positive one, you could take the positive and divide by all, including the positive and including the negative. So the results you have the is the accuracy. Okay, so let me get to the document so I don't miss anything. So evaluating the performance of a supervised learning model is crucial to ensure its effectiveness. So several metrics are commonly used depending on the task classification or regression. So here we focus on metrics relevant to classification. Just leave this. So let's go. So accuracy, the proportion of correctly, yeah, this is what I mean. The proportion of correctly classified instance out of the total number of this thing. So this is maybe all your email. You now take the proportion that is spammed, okay, over all of them. This is, I'm setting example with this now. So this is for positive though. So TP is for positive and CN is for what? True negative. So by all of them, so if you sum up, it will give you the opposite accuracy of this model. For precision, the proportion of correctly predicted words predicted provides instance of all what instance predicted. Just don't leave the English, but what it means that is how precise your model is to what. For the precision, it means, let's say we take the predicted value and the actual value. So is it a precise? Is it the same with the actual value? So that is what it means. And this we call is sensitivity, how sensitive it is. Just a slight change can cause a whole lot of things. So that is what all this English here means. So let's get to see coding example. But before then, you have a question to that, just so that when we get to see the coding example, maybe I should take out to get some questions, or where I should go back, because after this we should dream. Or I should even ask questions. How many people are here? See Sandra, see Promise, and Esther. Okay, so I'll be going one by one. So Esther, who came first? Esther just left. Promise, you were in the last class. I think it was Sandra who was not there. How do you detect if a value is could be grouped or classified into regression or classification?
Okay, regression actually gives like a particular answer, like one particular answer, while classification would give you like for example, maybe you're finding a weather, like you want to get the value of maybe the amount of rainfall, something like that. You can use regression to get the amount of rainfall. Now, maybe if you want to predict, for example, you're like, what should I use today if it rains? Something like that. You can be like a kind of grouping. Did it rain? Something like, I don't know how to explain it, but classification gives you a group of answers, like grouping different groups. And it
So,
happens with when you are using, they can use labels for that also, and then it will give you one of the labels as an answer. But if you are using regression gives you an actual value. Like, that's what I can say.
okay. Okay, so that's beautiful. Sandra, can you put something?
All right, you said recreation has to do with
I'm sorry,
numerical data.
stop sharing screen and you put it not call me to that. How did we get there? Go ahead.
You said regression has to do with numerical data, while classification has to do with groupings like total number of each item grouped together. For instance, maybe let's say, for instance, number of balls, number of houses, like grouped.
Okay. So what are determining factors or examples? What are they? Okay,
So
let me
when
know.
it has to do with numbers, it is for regression. Then when it has to do with grouping, classification.
Okay, so the questions is between label and feature, which one is an independent factor?
I think label.
Label is independent. Okay, promise you
Mm,
between label and feature, which one is independent?
I think label is dependent on feature.
Label is
So
dependent on feature. Okay.
dependence on feature, yes. So label is the dependent factor while feature is independent.
Okay, so that is beautiful. Features, just some technology, but these are examples. So, and they are the determining factors. So, what that means is that um, the output itself depends on those factors, right? So, okay, so that is that. It always give us an issue. So, I have some doing that here when we look at it. What are these? I'll just take my time to explain for us to understand better. So just do a line by line explanation of that. Okay, so yeah, so this is it. I discovered that while when we type in the class, due to lack of time, it shows more errors and it's needed to prepare it and get. Okay, and this data set is just a very simple example that I'm using. I did it this morning. So in your own case, you could get a data set online, or maybe you could still work on the iris data sets though. But I just need to get this. Of course, we've been working with data frames like Panda, so you know what this is. But in your own case, you can visualize it or feature it as how should I say a data set. Okay, so this line, of course, it imports pandas. We've been using pandas, and this is its popular alias. And sklearn, this is what you'll be splitting the model into test and training. In our own case, we're using 70-30, where we use 30% to test and see, and we use 70% to train the model. You are well familiar with this because we did it. It's something you've done even in your projects. And for this is a decision, this one is for decision tree, right? It's for decision tree, you get to use it. And this one is for random forest. I told you when you see as assemble, it has to group everything together, assemble all the trees. So it's for, once you see that, you know it's for random forest. So these matrices where we saw is for the accuracy, the precisions, and all of that. So the accuracy score where we talked about. And the math plot slip, you know what is used for visualization. I needed to, it was just optional though, but I needed us to just visualize what we did. So these are just the important one. Even without it, it will get the work done. Okay, so let's see. So this is me creating my data sets. You understand this one we've been doing. And for this, you know that this is a Python dictionary with key and value pairs. And from here, I converted the Python dictionary into a pandas data frame. So if I could print this out, you could see if I print df, I don't even need to, of course, you know what that means. It's organizing into 2D arrays, like in rows and in columns. So that is what it is. So I don't need to do that. Okay, so split feature stackets. So this is where we get this to use this model that I imported, this test trends with, use it and you know it. So this is what happens here. This is where we get to talk about the determinants and the words, those that are independent and those are, or we could call it feature and target. So this, when I made mentions of features or example, this is it. So now this purchase now depends on the age, maybe the age of what, let's see, use house, and we're using the age of the house and all of that. So it determines what will be the output. So in our own case, these are my features or my examples or my determining factors, however you want to call it. And these are my levels. This is my level, my targets. Okay. So of course, I told you that I'm using 70-30 to train. This is it. I use 30% to train the model. You know what your X train, how should I say? Your X train, Y train, X test, and all of that's what they do. So now this age now is in my own case, what this age does is the age of the customer inside this data set, and income is my yearly income. Let me just put it, and target value, one is for years and all of that. So when we talk about binary, I make mention that it's for year ones and zero. So this age now is for the age of my customer, and this income that you are seeing here, which of course is in this my data set, age, income, and purchase. This is income is, let's say, my yearly income for customer, and what's my purchase is my target value, and of course, you know, it is ones and zero, as you can see. It's, as you can see here. So what's the next is this X train. Just take my X train and move over to Y train. So this is for 70% of training that I assign it for. You can see 70% for train, and all the tests that you're seeing is for 30%. And for my X test and Y test, all are 30%. So now this 32 now, 42, I like using this random 42 ensures that they split, like what it ensures the split is reproducible each time. It's reproducible. You did that in your last project, so you know what this means. Another is for my Another after this, I'll get to my decision training model. So this is it. I need to put them in sections and for you to see. Okay, so for my decision tree model, this DT, this particular line that you're seeing here, is when I initialize and train the decision model. And what this line does that I created an instance of the decision tree classifier, right? This instance now. Then I now use my reproducer, making it reproducible, this states, random states to be 42. What this aims is that it ensures consistent results depending on how many times you run it. I'll run it and you see it. It ensures consistent results. So this model that fits this particular line is where I train the model by giving the training input xtrain, right? For training input, and the correct answer or is what ytrain, which is what your, should I say, future and your target do. So what is those that I feed xtrain for training the input, and the correct answer is my ytrain. So it's what it will compare with. So this line is where I predict the test, and for this line, I use the train model to predict whether each test customer purchase or not. So if it's purchased or not purchased, it falls under what's now classification, which is in category. So this particular part now, based on by what I've said now, it shows that it's what's a classification model where it will test where the customer will purchase or not. Okay, so you could see accuracy. So this is where this comes into play. This module comes into play. So I calculate how many predictions were correct. You could see decision tree accuracy. I'll print it out for you. You calculate how many decision tree were correct, and accuracy of 1. If it shows 1, it means that it's 100% correct. So an accuracy of 1, it's 100% correct. Okay, so let's see. So from here, which is print out this line. Okay. I lost network, so my network is just back. I hope I've not lost you. Okay, so that one is correct. That's take. Runtime disconnected, connecting to person. Okay, so it's runs now, correct. Get this one. Okay, correct. So that is when we run this one now to give us, have you seen it as giving us what? So the decision tree accuracy is 1. Of course, we look at accuracy, what it means. And accuracy of 1.0 means that it is 100% accurate. Okay, so these are the precisions, okay. predicted positive instance out of the actual. So this one is correctly the number of correctly predicted instance or correctly out of all the instance. And of course, the prediction is a proper harmonic mean precision. And what it means is that it states us recall, which is, of course, you know that how sensitive it is to produce instance. So multiply by that all over the correct precisions and the, so when you sum this up and divide by this, don't worry, I'll give you a material that visualize this better for you. Okay, so that is what we aim to get here. Okay, now, so this is for decision tree. You could see how simple it is, just one way. Now let's get to C for random forest. Now, just for me to add, so I don't forget the F1. The F1 is a balance between precision and recall. Just trying to balance this, what you're having here. It's a balance. You could say that it does not really change this much. And this recall, it's for sensitivity. Okay, so it's just a balance between precision and recall. So that is it. Okay, so let's get to see how random forest is. So this I initialize and train the random forest model. And for this first line, I create a random forest model with 100 trees. That is why you're seeing, and I still remain my consistency of 42. Okay, so this 100, of course, you saw this, that this is an in what a parameter. Yeah, saw this from my documents where random trim coming. Yeah, this estimator. Sorry, how long have you lost me? I didn't know. I was just talking to myself. When did you lost me?
What? It's 7 minutes.
7. Jesus Christ. Ah, I asked question and no one responded. I was like, okay, so let's go back. I didn't know. Sorry. Where are we? Where are we here? Did we get to, at least were you with me where I get to talk on the random forest model?
You are just started.
Are you serious? That means it's up to 7 minutes though. It's really up to 7 minutes. Wow. Okay, so what I said is that this is for decision tree, and we've seen that the accuracy is 1. Okay, but when I get to random forest, which explore a lot of options, a lot of examples, a lot of checks, just like the scenario I gave where you get advice from one person and the advice group or team of people gave to you, so it will be more accurate than this. So this is 1% of it, and from what we've seen and from what we've discussed over, we get to see that the accuracy of random forest should be either 0.6 something or 0.5, about half of this, which shows you how correct it is. And this value should be almost half of what you'll be having here. It's either going to be 0.5 or about 0.67 or something like that. But just as to show you that it's more accurate than decision tree. Okay, so here is where I initialize and train my model. So this particular line, what it does here is that it creates a random forest model with 100% with you saw these parameters now in our documents, which shows that, where is it, parameters. We saw this n estimator, the number of trees. Just leave trees because just a number of examples, but I just used forest or trees to denote the concepts you're working on. And max feature, the number of features to consider when looking for the best plates. This feature, of course, you know that examples, there are a number of examples, it could be number of examples, numbers of checks, just assembled to look for the best plates and maximum depth. So we see all of this here. Okay, so this n estimator, the parameter that you saw, the equals to 100, shows that I'm using 100 trees, or you could say 100 examples or features or checks, but you just explore yourself to a lot of things so that you get to assemble them and get a better or more precise or accurate result. And this random state equals to 2 shows what consistency. Okay, that's no matter how many times I run this, it will still be consistent with the output. And I usually use it 42. So when I use this, so it makes it more stable, the results. And this 100 it shows is that I'm using more examples. So in our own case, we're talking about forest here, it means that I'm using more trees. So this part is where I trained my model using the training data that we have. Okay, so this part predicts is what you predict the test. So it predicts the value on the test using the trained what random forest model. And this is just for accuracy where this model comes into play. Where is it? Where here this one matrices where we saw accuracy, precision, F1, and recall. Okay, so that is when we this that's that that is working here now. Okay, so it checks for how many. This will just return how many predictions we correct. And I didn't know, I ran the code when people were off. So we saw that it is, at this end, it's almost half. I said 0.5, but this is 0.6, almost half of this. So it's 0.4% away from this. I don't know if what I'm saying. So you could see from this, it could be 0.5, 0.6, or 0.67 somehow. Let's see. That shows you that it's by half more correct. You see accuracy and this. And you know that this F1 is a balance between precisions and recall. Most of them are 0.5, 0.5, look at 0.6. And so these values just tells you how accurate the random forest will judge more than a decision tree. And this one is just optional. We'll work without it, but I need to show you. So it will just, what this does, that you read it. This is about matplotlib. You could see plot title, plot show. So this is matplotlib trying to visualize the data, what we've done. And I did it only for decision tree. Okay, so what this line does, you know it already, but let me just take it down. You'll be working it. Okay, so I create a blank, we just create something like a blank canvas like that. And this H are just feature labels. So it will fill with labels outputs, where is it? It will fill with label class, and this class name are the labels outputs, which yes or no. So this fill true, you add color for virtual visibility. So that is how I said it's to true. And what again? Plot.show will just show the, we just display the chart. So we've been working on it. So I ran it. So it wasn't I was asking question, I discovered the open way not there. So decision tree visualization for this, where is decision tree for this decision tree. So let's see if we can get something about it. So age less than 30% and all of this. So these are in the values from our data sets. Where's the data sets? Okay, so when it's you sum everything, this like from here, it will sum everything up. So that's why it's giving this value 37. And sample, how many are they? With sample values, this 7 from the results 1, 2, 3, 3, 4, 5, and it uses where is it 0.2. Okay, and the value was H plus is on. Okay, so this actually it illustrates. Oh, now, okay, now let me check in a very simple illustration using the microfinance that could work here better. This could be our credit history. So if the history is good, could be true. If the history is bad, could be false. So from years now, it's been, could it be owning? Like maybe could it be owning from the previous loan, could set it to true. And if the credit history is false, that means it's bad, it's owning, it's not true at all. That means it's owning the company, right? So I'm just trying to relate it to real life. So basically, this is example where we get to see in practice how to work with decision tree. You could see the accuracy and working with random forest with plenty examples, or you can call it features. So this is just that. And yeah, this is, it's advice you always set your, how should I say, set these random states, just set it to any number. What this means that it maintains, it makes it stable by ensuring consistency. It's make it stable by ensuring consistency. So that is that. It might not really make sense as this is the first time. So what I'll do, I'll give you some materials to read and maybe example to work on, which will make you read and get to understand better.